Our next speaker is Ernesto Lupercio from CINVESTAV, and he will give a talk about entropy and knots. Thank you.
Well, thank you so much. This is a kind of a very relaxed talk. With other people, several people have asked me to say, why would you want to know anything about knots? Why is all these people talking about this thing? So my talk is very relaxed. I will report a little bit on our progress, but I will mostly be very friendly and explain to the people that are more of experts in computer science and other aspects why the topologists and the mathematicians and the physicists would want to know something about these things, the knots, and why it could be interesting in both directions, back and forth. The knots could inform the machine learning. Not only the machine learning could inform the knots, so it could go both ways, because it's this kind of very nice universal problem that has very interesting properties. In many ways, let me just say the phrase universal for quantum computing, but I'll get to that. Right. Well, anyway, this is our team that have been working on this project for a while. This is the first time most of us are in the same room, because we're located all over the place. So this is the very first time most of us are in the same room. And so it's us and Ramiro and Carlos and Pedro and Edison. And you will have to ask them some of the things that I So it's a picture from Wikipedia. So what is a knot? So what is the basic thing is that for a mathematician, a knot is this kind of piece of cord, but that is united at the beginning and the end is the same. Of course, you can knot it first and then unite the beginning and the end. But it's just this kind of topologists say it's just a circle, but the way it is put inside space is what it's interesting. And if you put it in dimension 4, this aspect disappears. All of a sudden, in dimension 4, automatically knots on knots, magically, So it's really a very interesting interaction between dimension 3 and dimension 1. It has this very interesting, this space and this knottedness. How do you measure this knottedness? This is an interesting problem. And of course, we're going to go for but well, engineers and biologists and physicists and mathematicians think the important problem of knots is slightly different. And here I would like to clarify this point. For the chemists and the people that are searching for antibiotics and all these kind of things, what they care about is not quite what the topologists care about. The topologists just want these two very complicated pictures and to know that one can be taken to the other. And the people in this kind of fields really want to know how you take one into the other. Not that it can, but how you go from one to the other is very important, the how, and to make it in a reasonably efficient way. You could very naively say that you want to minimize the number of chemical reactions that you do with these very complicated molecules, the topoisomerase and the topoisomerase inhibitors, etc. You want to know the how. And the mathematical problem of the how is a gross simplification of the biological problem, nevertheless extremely helpful to guide you in this antibiotic search, etc., etc. So even just knowing that, but mathematicians are often a bit too smart and they say, oh, I know for some really theoretical reasons that this thing is this thing, but you don't know how, Well, so it's important, this difference. We want to know kind of the how also. So could we play this video? Maybe I load it here. So again, for the people that are not so used to the field, well, this doesn't play. Codec unavailable. So it was how to form the knot 6-2. You won't have it. Sorry. The video didn't copy from my memory. but it was how you noticed. But this should be the outcome. Anyway, let's worry. Here, this one works because there's a and here you have the idea of, for a mathematician, all these things are the same. And just the same, just indistinguishable. Of course, for the biologist, you want to know the sequence of, you want to know the sequence of moves that takes you from one to the other. So something happened here, a move happened, a cross happened, something crossed, da, da, da. You want to know all those things. You want to know the sequence of moves. So this is the unknown, but it looks very knotted at the beginning, doesn't it? But for a mathematician, this is the unknown. Was never knotted. But for a biologist, it was quite knotted. And then you unknotted it. You see what I mean? So, so we, our team has worried about this problem that is closer to the biologist's concern than to the mathematician's concern. So
I'm just going to interrupt for a second. But it is unknotted, right? If it's DNA or something, it will still transcribe, right? So, are we just like thinking about like the complexity of like embedding?
yeah, we care about the picture. We care about we're lying when I say knots. It's not theory. What we're going to do is going to be diagram theory. It's the knot diagram. We care about the knot diagram, and so it's much more in the spirit of Carlos's talk, where we have there is this formal language when a proposition is the diagram itself is this text, and a Rademeister move is a logical valid thing in a language, and a proof is to take it to the knot, knowing that it was a knot. To take it to the knot is a proof. And so you have this branching and the kind of thing. Same as in Carlos, exactly the same as in Carlos' stuff. And so we were laughing at Carlos' stuff because everything that he had to overcome, we had to overcome in a slightly different way. But you get to the same problems over and over and over again. But it's extremely close. And we have been very inspired by his previous work, Carlos' previous work. And also, I should mention your work, of course, but also Gukov's work that has been very inspiring, and all the things that he has done. So, and many other people's work. But you mentioned a lot. I send the people that look into the video to your talk so that they see the references there. This is a very popular talk that I'm giving here. Anyway, this is, we want to understand the book. And notice that when this happens, the first thing that happens is these crosses. Well, this is a continuous thing, complicated thing. So what you do is you discretize it, you make it into a combinatorial problem. And so you say, well, this is the first thing that happened in that movie. It's the so-called second Rademeister move. And then these things happen, and these things happen, and these things happen. And in that movie, that's all that happened. Combinations of those three things happen, and you discretize. What happens in between, okay, you have these very important moments where two things cross, or where this crosses, or where this unwind. These very important moments are what you want. You want this sequence, the discrete sequence of moments to describe the whole movement, and you discretize it. And here you have an example. Then you have this to here. And then this is, well, non-obvious. You know, if this is a game, take this to this. Give this to kids, they will do it, because they will do anything. But you need to be rather clever to get from one to the other. You have to be clever. This is a proof in this language. This is a proposition in this language. And then you need to encode this in letters or some way, in some things. I'll explain how we encode this thing. There's many ways to encode this thing. And not all the encodings will be equally amenable for machine learning. And you have, in fact, we thought very hard what encodings to think about to be amenable to the architectures and so on and so forth. But here you have a typical proof that this thing is this thing. And we care about the proof. We not only care about the result, but we care about the sequence, the proof. Okay. For some reason, this example is not famous. Wolfgang Haeckel's Gordon or not. it's still not. But it looks rather not, doesn't it? I mean, it looks like there is some complexity here. So it's, let me say that the circle has low entropy. Let me just say that the circle has low entropy, and that this thing has high entropy. There was entropy in the title of the talk, wasn't it? So let me just say that this has high entropy. This diagram has high entropy, and the other diagram has low entropy, and I want to minimize the entropy. Well, again, this was a nice proof that this was not, but this will not happen. Ah, no, this will happen. Well, you watch it 40 times. I mean, it's not, you realize that. For some reason, this thing should have a little look here to show that really never broke, but well, whatever. And, yeah, and everything is just Rademeister moves, really. Again, if you think about it, again, it's kind of funny. Everything in these movies that you do is just a combination of these things, these local portions that we saw before. These local, notice that these are very local movements. They happen in a little piece, in a little tiny piece. They are local. And so, well, the thing is that, of course, we have been talking about this one only. But, as we discussed earlier today, there is a lot of them. There is the only one with 0 crossings, and then there is the one with 3 crossings, and then there is this with 1 crossing, with 4 crossings, 5 crossings, and 6 crossings, and 7 crossings, and the thing explodes rapidly. There is more, the more crossings, the more truly, what does it mean that 8-7 is not 8-8? It means that there is no way to deform 8-7 to knot it into 8-8. Of course, 8-7 has many possible diagrams, but not this one. So it could have many diagrams, 8-7, but you'll never be able to get to 8-8.
What's the first case where there's two that we don't know whether they're equivalent or not?
Two what?
Two knot diagrams like that with some number crossing the same number, let's say, or even different. We don't know whether they're equivalent or not.
Well, as far as I mean, I think this should be rather quickly that we have no idea. You know, in the knot tables, how many crossings do we get with the knot tables?
No, I mean, there's 1.7 whatever billion knots with many crossings, and there's like.
But have they all been distinguished by the variance? Oh, okay.
Oh yeah. But it's still only 20 crossings, isn't it? I mean, very quickly you.
That's right. But there's a famous pair, the Perko pair.
Oh yeah, of course.
That's like a joke that it's not a joke. There was a mistake in our tables, and it was discovered by Ken Perko, who of course has a math degree and did work with John Berman, but like he's a lawyer. So he just continued working on it, and it's the same number of crossings, and it looked like there were different knots, but they're the same knots.
Very highly non-obvious. I mean, it was by knot invariant that they suspected. It was by knot invariant that they suspected. So
But when they say knot tables, does that mean that they've distinguished each pair of?
Yeah. The knot tables is all the ones that a minimum number of crossings state, they are here. All of them.
But somebody has distinguished every pair of things by invariance. But there must be a point at which we don't have enough invariance to distinguish two things. No?
Not yet.
We don't know. You know, 15 variants seem to be quite complete, but we don't know. That's part of the fun.
We don't have a complete table.
And of course, and the thing grows just like crazy, and even the number is very mysterious. So here is, for example, all this, but this we know. 9 crossings, there's only these ones. But then, of course, there's infinite number of diagrams, and this is the minimum number of crossings. A knot, you can project it, and you say it has 9 crossings. The projection with the minimum number of crossings is 9. But it could have a projection. The knot has all these projections with million crossings. Is there not? So, you were mentioning at 12 crossings, 1,000 million or something, I don't remember the exact number.
That is only 3,000, that's not enough.
About 20 crossings, I don't know, you go to 1,000 million. But this is only the simplest projections. Imagine the problem that we're dealing with, because just the unknown has all this infinite number of diagrams, and with the number of crossings, the projections of the unknown that has 20 crossings is already brutal, and this is just the unknown. So we're dealing with a hopeless problem, and we'll see exactly how hopeless it is. So, more precisely, Rademacher's theorem says that in the 1930s, he gave the first proof that there is knots that are distinct from the knot. And he did it by showing that all knot deformations can be reduced to these three Rademacher loops. And if they're on all the movies, you will see only these three things. In all the movies, you will only see these three things. It's a theory, it's true. So you will see only these and these and these. And so you could have a language of we'll see it of a Gauss diagrams or whatever, and any encoding of the knot. And then this is a word, and then you have these three moves. But this has the problem that it's not, the probability distribution is, well, it's mysterious. What is in a path, in one of these movies, what is the typical number of moves 2 versus moves 3? What is the probability distribution? Same question. What is this probability distribution? We want to know this probability distribution. And it's very bad for the Rademacher moves because they are very inexpressive. It's like it's like assembly language for knots. We want to do a higher level language for knots that has more of a zip law. Think about it if you take the big book El Quijote and you see just diagrams. They don't have a very good zip law. Monogram, I mean, letters don't really have a little bit, but the A, the E, and it's not really a very pronounced zip law. But now you do words, and half of the words appear only once in a Quijote. Now you have very expressive, it's a very expressive thing. And what we have discovered through our experiments that there is a kind of a much better way to deal with this thing, this theorem, that is so much more expressive, that has so much better kurtosis in the probability distribution, enormous kurtosis in the probability distribution that is so much better for our techniques. This is the gist of this talk. That's the point. Okay, but just that you get a little bit of the idea of how bad the situation is. There's this beautiful theorem of Coward and Lackenby in 2010. They take two diagrams of the same knot. And both have less than 10 crossings. 5 crossings. Both have less than 8 crossings. Both are, you know it's the same knot. You applied all the invariants and you super suspect it is the same knot. But because you applied all the invariants, they give you the same. And now you are super sure this is the same knot. But it has less than 8 crossings. But now you want the path, don't you? You want the path. You really do want the path. You want the proof. The formal proof. Well, this tells you how hard this knot is. Then there exists a sequence of Rademacher moves in less than Rn moves, where Rn is, how do you pronounce this? To the end, where the number of 2's is 10 to the million n. So if it was 5 crossings, it's just 10 to the 5 million, 1 and 5 million zeros, the number of 2's, and then to the end, just to cap it off. And just for 5 crossings. And we don't know better. This problem is impossible. You don't have a right to solve this problem. And that's why we decided to stress machine learning to the limit. Why? Because it's impossible. So can machine learning do anything here? Can you do anything here? I mean, That's the whole point. This is the theorem that tells me, oh, this is interesting. Because we want to know this path in certain sciences. And that's why mathematicians kind of give up in knowing this path, and they say invariant and all this other philosophy. Well, what we need is a Maxwell demon, If we have this Maxwell demon that that you took, Maxwell demon, you have this node with a high, this diagram with a high entropy, and it just told you what, and you have all these possible, you have all the local places. You can count all the local places, it's not too bad. And now you say which move to do, 1, 2, or 3. And then you say, Maxwell's demon says you touch here, 3. 1, 2, 3 or nothing. You have 4 options. You touch this local place and it tells you 3. It opens the door for you. And then you solve the problem. You have a Maxwell demon. The problem is that you have to super violate the second law of thermodynamics badly. You have to grossly violate the second law of thermodynamics to do this. But you need a Maxwell demon. And I think of these, even the most innocent of these things, as Maxwell demons. I think of them like that. As these machines that just like life seem to locally violate the second law of thermodynamics. That's how I think of these objects. So there, well, this is Boltzmann's equation, S equals K dot L of W. But you probably in this crowd know this equation better in terms of Shannon's formulation of P log P. You probably know P log P better than K log W. Same thing. Anyway, there is this other concept that you all know very well. That's called Kolmogorov complexity. You fix the rules of the game, and then you count your shortest program. You fix your language. Now, Kolmogorov proved that it's quite independent of the language. So that's another story, in a certain sense. By the way, Kolmogorov complexity, K of X, measures the amount of information contained in an individual object, string, by the size of the smallest program that generates it. It naturally characterizes a probability distribution over the set of all finite binary strings, assign a probability of C2 to the minus K of X for any string X, where C is a constant. So you have, and this is a universal probability distribution. This is a universal probability distribution. And we had this problem. All I have said is that if I had this probability distribution, I won the game. If I had this probability distribution, I won the game. In fact, if I do an encoding where the probabilities of the moves are quite different, unlike the Rademeister moves, I'm already kind of winning the game. I made encoding to own to the information theory. Okay, so the Shannon entropy of X of a random variable X is a measure of the aversion. The aversion certainty is the smallest number of bits required on average to describe X. The output of the random variable X. That's the Shannon entropy. Well, the Shannon information, or whatever that it's identical to the Boltzmann equation. And well, Kolmogorov complexity and Shannon entropy are conceptually different. You think of them kind of, but if you take a profoundly difficult assumption that you have a recursive probability distribution, and we are not assured this. You have a recursive probability distribution. Namely, distributions are computable by a Turing machine. And we don't know this. Or, in fact, we suspect for these problems. But anyway, let's ignore that part of the theorem that will raise this. The expected value of the Kolmogorov complexity essentially equals the Shannon entropy, up to a constant depending only on the distribution. More precisely, so you have this Kolmogorov complexity, you have this Shannon entropy, and well, you can say, well, I wanted to do entropy for the nodes, but maybe as a proxy for Kolmogorov complexity. Kolmogorov complexity is what I want to compute, if you think about it. In this proof system that that I'm talking about. So for any recursive probability distribution P over sigma star, the average value of K of X and channel entropy satisfies it. Well known. But only for recursively computable probability distributions. Well, with no good reason, I will just act as if my probability distribution I'm after is recursively computable. Probably it ain't, you know. But anyway.
This recursive computability, is it related to Markovian property?
Oh, Markovian property, I'm going there. Well, so there is an example of success using this technique. There's all this Rubik's Cube with deep reinforcement learning. Here, but it's what Carlos was doing. And he talks, you know, you have the policy, the value, what do you call it? The value and the policy. And the value is the distance to this Kolmogorov complexity here. The value is the Kolmogorov complexity. The policy is what move you're going to do, what element of the group you're going to apply. But this is a much easier problem than Carlos' problem, or the knots. That is hopeless, you know. But well, you can do it, and then you solve beautifully. So, but not only you start getting these emergent properties in the Rubik's Cube.
Are they doing Rubik's Cube of kind of arbitrary sizes or something, or just a 3x3 bit?
You just do the usual one is article, but if you bounce the size, that's okay. If you don't bounce the size, then
How do we know that a node in these structures not faces the causing problem?
how do we know that what?
That we are not the structures that's like dissolve these nodes, we don't face the causing problem. How do we know that it's going to come to an end?
Well, because of the thing that I told you, we know because of a theorem, highly non-trivial. I mean, it ends one day, you see. There exists this path, the proof exists there. Well, even the theorem of Rademacher says that the proof exists. Or everything is decidable in this universe.
No, but that doesn't tell you the bound on the side.
No. This gives you a bound. And of course, this means that you cannot encode addition and multiplication at the same time in this language. Interesting. Addition you can encode. You see addition, you cannot encode in this language addition and multiplication.
Why? What does that mean?
Well, then you would have an undecidable proposition. But here everything is decidable.
How you computed this number without more or less solving?
No, you compute this problem solving, you know. I mean, this is an algorithm. Problem is it grows a little bit fast.
Yeah, but it's a constructive.
It's totally solved. It's an algorithm.
But it's constructive, the proof.
Yeah, it's constructed well. But it's not such a nice algorithm as the one Carlos presented for his problem. He had this dynamic programming. We don't have this dynamic. We have this, you know. We don't have this dynamic programming. We have this instead of the dynamic programming. So, but in the Rubik's Cube, they don't use that. What we use for the Rubik's Cube is we do the most stupid thing in the universe. That is, you scramble the cube, and then you break the glass, and then you assume that it assembles itself. You violate, by definition, the second law of thermodynamics. You break. But the cube is a very small term, it's a tiny problem, you know? Yeah.
But taking the entropy is not just like basically 1 power of 2.
Taking the entropy.
The entropy is a logarithm. So it's a random. It's the average of logarithm. So you have like the number of possible options is 2. That much. So taking a logarithm, take the average.
No, but remember, here the theorem is stated in a mathematician's confusing way. It's just about.
Okay.
We don't know. No, these have nothing to say.
So the Hassel variance equivalent proved that computing the unlocking number means how many crossings you need to change from this to this in the amplifier. So,
Yeah. That too. But this is.
Yeah.
Yeah. Well, no, I don't know what it was. Yeah. But, it's miserable, all this thing. So what's going on? Well,
Actually, that theorem that you just showed, isn't that the definition that it's the same node?
the theorem that I usually is a theorem. The definition is that they are connected by a nice term, so you want to take that as a definition.
So the theorem is actually a definition of the same node if there exists a series of wider Master-Schreier moves. So that means that's by definition, no?
No, but the theorem gives the bound for the number.
There's the bound. Can't feel. It's
Very
actually
high
hard.
bound, yes, okay, but a bound.
A bound, very bad bound. But anyway, probably it's very bad. And what we're seeing is very interesting. And Siroya is seeing something similar with his methods and with our methods. What are different methods? Let me just say more or less what we're seeing.
Just one more. Is quantum makes it easier to find the.
What?
Is quantum makes it easier to find the bound?
Yeah. Well, quantum makes it. This is a classical algorithm, so to speak. You can do quantum constant change. Well, let me tell you what we're finding.
But it's a good question. What's the bound if you allow quantum algorithm?
They know, but I don't know. They know. Yes,
It's very relevant if you want to use it for cyber, for a one-side function. If you want to use it as a for KPC, it's very important to know the bound.
Yeah, but anyway, but let me say what we're finding. Let me give some of our very stated results. We're finding something very fun. We're finding that there is this smart modes. In fact, it's a sequence of modes. You know, there is kind of these sequences of modes, and then there is this kind of sequence of modes that is very smart. And that almost never happens. And so, let's for good nodes, it happens once in. How many times? Once in what?
1 per 1,000.
Huh?
1,000. 1 per 1,000.
The four, no,
The
that's
forecast,
possible.
the
One in
forecast.
100,000 or something like that.
Yes.
100,000, and you do this kind of super move. Fly, and you get into a new realm of diagrams.
Magical move.
Yeah. And then, but then, there is this fractal structure. You see, if you have this, that knot diagram, you can take a little piece of the string, and you can just twist it a little like this, and then do all the unknots here. At every point, all the unknot diagrams. At every little arc, you can do all the unknot action. So if you think of this as this graph, where the vertices are the diagrams, and the edges are the moves, you have this fractal structure, where at every vertex you have as many branches, identical branches of a graph, as arcs in the projection. And then at every arc you get all the, and then you get all this fractal structure that just moves intensely. And but these moves for them, not I call them the vacuum fluctuations. Just these are not things. I call them the vacuum fluctuations, and we declare them to have very little energy. These vacuum fluctuations, if it is just a knot, you will make it very, very small, and it has very little energy. And then there is the important ones. But you have to deal with all these.
So the definition is something like if you can make a circle and cut your diagram, and the inside of the circle is the unknown, then
And so you have these vacuum fluctuations. And then you have the high energy, and then you have this super high energy.
But you're talking about really a circle which only cuts the knot in 2 places?
Well, you take the knot, you have very knotted position, and just do a circle to any arc.
Yeah, but so that's going to create a diagram such that there exists
A node.
a loop, I mean a circle, not a circular circle, but a circle, which only cuts the diagram in 2 locations, right? So you can tell what you can.
Yeah, when you take this long knot and make it not surgery. Yeah.
But you do
Each
each
node works on.
Huh?
Do you do, do you just do two or do you do four?
For
Do you do two triangle thing or do you just cut it so there's two angles?
well, yeah, I just cut a little segment, and I make a long knot that is a knot, and I just glue it there. And I do this everywhere, and I get this kind of Berkovich kind of picture. Just there, everywhere. It's just this fractal thing. And that's not the worst. I mean, you have these other regions where you could do the same in other fractal structures. But it's super fractal the thing, but you have a renormalization group. And as you saw in this interpretability language new paper, they were detecting this automatically, right? The architectures, the transformers were detecting the power loss and the renormalization group and all this story. So anyway, Rubik's Cube in comparison is a finite group. Tiny, not. You just have to compute some commutators and nothing. Nevertheless, same strategy. Actually more similar to, more nearly following really Carlos's strategy. Really.
Well, that was AlphaGo strategy, so.
AlphaGo strategy. Anyway, there's many encodings for knots, and there is the Gauss diagram of knots. And what is a knot diagram? How much time do I have? Sorry?
Until 3:30, so you have 20 minutes. Oh, but you started a bit late, so
Okay.
maybe 25 minutes.
Then I can explain this. So this and this, 1 and 1 bar, is just this crossing. And plus means that this one is above that one. That if I go counterclockwise, I go from up to down. And this is what plus means. Counterclockwise from up to down. Minus 3 means that counterclockwise I go from down to up. And so I can present a word that is, I put here mark point at the very top. And then I have this word that is 1 bar, 3 bar, 4 bar, 1 bar, 2 bar. You know what I'm doing. And I have that word. And that text is that non-projection. And then, of course, I have to add things that are not Rademaisterian, like rotating the thing, like changing my mark point.
If you go from 1 to 3, then go clockwise, not counterclockwise. Maybe I'm wrong.
It's okay.
From 1 to 3, yes, I go clockwise.
Because you
But it's at the crossings that I'm doing
Yeah,
this hand
it's
thing. It's at the crossing that I'm doing the hand thing. It's at the crossing that I'm doing the hand thing. And so I have these kind of segments. Well, but I have these words. But of course, I also have to give you the signs, the sequence of signs. So somehow I have to tell you, maybe before every number, whether this was a positive or a negative chord. And then, I don't know, I messed it up, but you know what I mean. So that word, that text, is that not projection, that text. And a Rademeister move does something, and it affects this text in a particular way. And so I have text, logical reasoning Rademeister 1, text, logical reasoning Rademeister 3, text, so on and so forth. And but now we saw that this is really very hard to navigate. It's really, you really are extremely lost extremely quick. Very, very lost very, very quick. If you have, without experience or training or anything, or mathematical training as a kid, I couldn't because it didn't exist. But if you did have a Rubik's Cube just as a kid, no training at all, you would you would have this feeling of getting lost very, very quickly. You do 2, 3 moves and now, what did I do? How do I undo my steps?
So just a quick question, I cannot resist. So this diagram, there's no randomized rule you can apply. So where do you start with that situation? I
Well,
mean, there's no simplifying, right?
you can do vacuum fluctuations.
Right.
You can do quick, and then you know, not a horrible knot here. Wow. And then fractal, you have a fractal things rapidly. And this fractality reflects both in the structure of the actual embedding and in the structure of the tree of reasonings. It's very strong, this randomized kind of thinking. And we're going to weaken it a little bit. So is it true that you could encode knots with words and you could encode the moves with things, not text?
Well, are there any axioms that need to be satisfied by the sequence?
Oh, there is a lot of axioms that need to be satisfied. Like this repeat, it's like parentheses, this thing closes to this, that, the signs are the same, one up and one down. There is a lot of, there is a grammar. There is a grammar, and then there is this story. This is a Wikipedia article. This is a story of how this thing, and it has semantics. Yeah.
I think in non-mathematical terms, what you're doing is you're tokenizing.
I'm tokenizing, and I could do one hot encoding here at this point.
Yeah.
But
you're tokenizing it just like Carlos was talking about tokenizing his stuff. Just like when we talk about transformers for words, they don't take the entire word; they create little tokens.
That's right. And
So
here you would want to do a tokenization of this story.
That's right. And that's why I think it's brilliant. Tokenization, Carlos was talking, I'm using different words there. Tokenization, and that's why you can eventually put this into transformer-like architectures because they take tokens.
Okay.
That's the brilliant part.
Yeah, and let me just say it even more poetic. This is a story, this is just a story. And it has its grammatical roots. It's a story. And there is these nicer stories, shorter stories. I didn't say something, but with the Rubik's Cube, there's this very intriguing thing that when you do it, you just were trying to solve it however you could. And the AlphaGo thing is even too powerful. Really, just for the Rubik's Cube, it's so simple that just the first policy, the value, the straight line one, will do it. Just that will do it. Because you just have 12 options, so you check the 12 options, you see which one to be closer.
Yeah. Of course, the policy thing is only done for speed. I mean, otherwise you would check all the different ones and calculate the value on all the different ones.
But here, all the different ones could be horrendous.
Yeah.
Here, you don't want to that. You really need the AlphaGo strategy. Okay. So,
Can you unknot in different ways?
Yeah.
Awaiting notarial.
For example, you can first unknot it very much more. Knot it very much more. And sometimes you are in the situation like the Rubik's Cube, really is a very good intuition, in which you feel that you're almost done. And to get there, you have to make it much more complicated before you can simplify it. You feel you're almost there, like just one piece of your cube is rotated, No, you have to make it much more complicated before you make it. You have to increase the entropy before you decrease the entropy.
But that means that there is a minimal length of the word, the final sentence.
Yeah, there is a minimal proof. There's a lot of complexity of the knot, the entropy of the knot.
Yeah.
If the probability distribution was recursively computable, Yeah, it was lambda calculus. Anyway. And this is good, and this is Gauss. So it's good. Gauss is good. I mean, this is pretty good stuff. Gauss is pretty good. But we're going to do a variation due to most of Yasha, most of our friends, in Chapolek, our friends, and One may think of a Gauss diagram as generated by the crossings of a knot. Similarly, any braid can be written as a product of crossings, that is elementary braids. However, in the study of pure braids, one has an often better option. Any pure braid is a product of full twists. Full twists are well suited for various problems, such as proving that the pure braid group is residually potent. This fact may also be stated as finite type invariant distinguished braids, which, of course, would be nice to know from us. Clasp diagrams are a variation of the concept of Gauss diagram, which uses full twists rather than crossings. And they have a much better, from our perspective, they have a much better linguistic C-block. Much better linguistic C-block. So, there it is. This is a clasp diagram. Well, it looks identical to a Gauss diagram, doesn't it? Absolutely identical. Gauss diagram. But this is the dictionary. This is plus is no longer that. It just, you literally substitute this by this by this, and this by this. You literally do that. And now you get a knot. Now you get a knot from a clasp diagram. This is a clasp. Another clasp. And now here you have the phi 1 knot. Notice that though I have 2, 4, 6, and 12, and 6, 20 crossings for the phi 1 knot. Have 20 crossings. But there is a dictionary, obviously. And then the theorem is each isotopic class of knots can be represented by a clasp diagram. This is not obvious, but it's true. And there is moves. But they are not local moves. They are global moves. And then they become so much. There's a whole bunch of Rademeister moves. A whole bunch of them. They are phrases. It's a new language. They're entire phrasings that are extremely compatible with knot invariants. All these phrasings are extremely compatible with knot invariants. I'll show an example of this very quickly, but really Basilier invariants, finite type invariants.
Can you say again what is a class? Sorry, I missed you.
That's a class.
It's a move.
No, it's not.
No, because it's the two pieces class.
Okay, I see.
So you have that, and now, well, here you have to convince yourself that, for example, the legendary 4-class move it makes sense. This thing. The thing is genius. This is most of it polyp. And so you have the theorem. You have the Rademeister theorem. But for these global moves that are so expressive, and so this is so much better. Well, we get the probability distribution, and we use Monte Carlo methods to get the probability distribution. We want the probability distribution. This is our way to answer this question. What is a typical diagram? What is a typical path in the space of these paths? So we use Monte Carlo method. Huh?
Sorry, this reminds me a little bit of some sort of ribbon graph.
Yeah.
So
look at this.
this creates a surface basically, is what you're saying, right?
Okay. And you have this cipher surface. For example, there you automatically you get the, well, it's not surprising, the Alexander polynomial is very easy. And really, a whole bunch of knot invariants are extremely easy on this presentation. And so Pedro is working on explainability. He's a brilliant undergraduate student. And so, well, you can learn some of these invariants. Well, he has learned them not. He has learned them not. So you give a text, like this text, and then it just tells you, is there not, or is not there not. So the question is, this architecture, what invariant is learning? Which invariant is learning? Do we know this invariant? Or probably we do. And because this is so amenable to this Taylor expansion of finite type invariants, it's a very reasonable question to ask, which of these invariants is this architecture learning with explainability tools? That's on the other hand, the strategy to actually get the moves in this infinite space that is impossible to do. Edison, together with Ramiro, are working very hard. And how is the path coming along?
No problem.
So
It's very hard.
it's very hard. It's hard but fun problems. Edison is doing that one, and etc. We are working on many aspects from these philosophical perspectives, all these various aspects that now we can attack from these different perspectives. But it's a very it's very much not really not theory that yeah, the invariants are a tool, but we want the paths, we want this impossible to find proofs in this formal system. Here let me explain the Alexander polynomial very quickly. You have this class diagram. Of course, you have automatically this cipher surface. And now you can do the L matrix is the linking matrix, and the E matrix is the sign matrix. Well, it's very easy to define this matrix, you know. And then if you just compute this matrix, that is this linking matrix and this sign matrix, you compute the determinant, you get the Alexander polynomial. So it's a very of course, there is the problem of translation to the node tables. Well, because the node tables are so small, this is not divided. But I mean, in general, computing the minimum number of crossings of one of these things is not a trivial problem. And just the minimum number of crossings.
So say that you don't know that encoding that's right there is actually following a pattern or it's running.
Sorry, I couldn't understand the question.
I mean, there you write an encoding in the board. So we don't know if that encoding is actually following a pattern or it's actually random.
No, it has grammar. It has a grammar. As I explained, the one has to close with the one, the top with the one.
Following always. Yes. There is no possibility
No,
of random.
there is a grammar to this sequence.
So I did not work in knot theory. I'm a geneticist. Oh, okay. Probably has nothing to do with knots, but
It actually matters.
My question would be so like in protein folding, right? Somewhat similar thing. They say, well, the theoretical number of bonds basically between all the nucleotides is, excuse me, the residues is very large, right? Like, but entropically, right? You would never see all of those, right? It sort of has this meandering structure as it's going from being a transcript to an actual protein. So is there any thought that there's some, like the intermediate structure as it's getting unfolded is...
Well, I'll tell you one of our results. I was talking to her about the result earlier. There is this unobservable diagrams. You have to be so brilliant to get to them that you'll never get to them. It's unobservable diagrams. They exist, you'll never see them. And then there's the observable diagrams, and they are close to the alternating. Close to the alternating. So there is something there. There is these kind of distinguished things, the alternating things that are there, that force automatically a lot of additional instruction on these sequences, and they want to be there. And then the other ones are perturbation of these ones.
Yeah, because I'm also thinking of like the traveling salesman problem. where it's always gonna find a circle or something like isomorphic to a circle in the end. But those algorithms, like you watch as they go through it, and some of the better ones, like they're not just brute force. They're you see sort of the bounds on the disorder as it's going to the solution. So this is why I didn't know, like if there was any thought of the boundedness on the entropy as it's approaching the unknown.
Well, we have labs. We're starting to think about, we're starting to think about this process, how this, what is a typical decay? All these sorts of things, we are only now. Well, first we have to develop all the language, formal language of this thing, the machine that does this formal language and blah, blah, blah. And sometimes we are scared that one of our functions doesn't consider a case or something. It's complicated. But modulo errors, we want to understand the decay of the entropy in one of these typical paths. What can you realistically expect, how to this thing to fold or unfold, so to speak. And again, the alternating nodes are extremely important, and they have all this additionally very strong structure, and it's kind of this skeleton that where everything builds up from. And the people that know nodes kind of have seen these things from their own perspectives, or being more probabilistic.
So did you try to have some sort of transformer learn this kind of grammar?
We are. Edison can tell you more about that fun. Yeah, yes.
I have a very related question then. If you're trying to have transformers that are learning the grammar of this, to have a large enough number of data from the transformer, can you randomly sample nodes with your this tokenization or representation in sequence?
I don't understand very well the question. We have the same problem as everybody does of a good sampling, but you're not talking about that, are you?
Like if you want to solve something with transformer, many times you want to have like 10 million example of something. Then sometimes you might wonder, okay, how do I get 10 million example? One way could be you can either sample at random sequences if you can represent your problem as sequences, but then you need the sequence to make sense of the problem. Or you could say, okay, I know that I have an NP-out problem, for instance, so finding a solution is going to be extremely complicated, but starting from the solution and going to the problem is probably P. And so then in this case, I can start from the solution, construct the problem, do that 10 million times in the hope that having the transformer try to learn the opposite direction works.
Yeah. That's what we're doing.
Okay.
That's what we're doing. Yeah. I didn't know the name of these words, but yeah, that's exactly what we're doing.
Okay. I'm still a little confused, right? Because like not every Gauss-looking sequence corresponds to a knot, and I don't know how to create.
Not every. No, you need. Not every Gauss-looking sequence corresponds to a knot.
So let's say if I give you a knot like 5-2, how do I get like sufficiently many?
I apply to it a million randomizer moves.
How do you know about like a random thing? Like I mean,
well, now that's where you do this kind of thingy. Some like Monte Carlo method.
Okay, just two things I want to say. I'll be quick, because I know everyone's trying to get out of here, but I'm not familiar with knots at all, so this is very interesting. But firstly, this does feel reminiscent of, like, I guess just the permutation group, right? We have like a finite number of, right? We have a limit on the number of moves, I guess, in the knots, right? Even though it's a terrible limit. And each knot in the intermediate step is equivalent, right? I don't know if isomorphic would be the right word here.
Isotopic, people say.
Isotopic? Okay. Yeah, so it feels reminiscent to the permutation group just in that sense. But also I was wondering specifically about, I guess, like the surface that we're encoding the knots on. Like, would like a 3 knot, I don't know. I guess like the invariance under like the different genus surfaces that the knots live in, right? So all of these like live on the plane, but do we have
Well,
this?
this one lives on a surface that is quite elaborate, doesn't it? Look at this one.
Yeah. So
Only the unknown things on the
okay.
Look at this one.
Okay.
Look at this one. It's a fun exercise to complete the genus of this one.
Okay. Yeah, I guess I'm just thinking like I can, like, even though yes, like the knot has like a higher genus, like no, I guess that doesn't, right? Yeah, okay, sorry, I'm just thinking of like in graphs is where I'm trying to make this connection.
So there is this graph. There is this graph here.
Yeah. Well, I mean like a classic example of like the complete graph on 5 vertices, right, has edge crossings on the plane, but it doesn't have edge crossings on a torus, right? Is there like an equivalent notion of that sort of thing here, right, where I can put like a 3 knot onto a different surface and it is?
Yeah. Just imagine having like a, sorry.
No, you answered that. I have no idea, but you do. So.
Yeah.
So just imagine the